In this lecture, we will discuss diodes and diode applications. A basic semiconductor device is the diode, which allows current to flow in only one direction. Diodes are commonly used for converting AC voltage to DC voltage and are called rectifier diodes in this application. This lecture covers the construction and operation of semiconductor diodes, how they can be switched on or off using voltage polarity, and introduces half-wave and full-wave rectifiers. It also introduces two special diodes, the light-emitting diode or LED and the Zener diode. Semiconductors conduct electricity less effectively than metals, but more than insulators. Common semiconductor materials include silicon, germanium, and carbon, with silicon being the most widely used in the electronics industry. Most diodes, transistors, and integrated circuits today are made from silicon. Intrinsic semiconductors are pure semiconductors, such as a silicon crystal made only of silicon atoms. Extrinsic semiconductors are created by adding impurity atoms through a process called doping. These impurity atoms, which have fewer or more than 4 valence electrons, alter the semiconductor's conductivity. At room temperature, intrinsic semiconductors behave more like insulators, while extrinsic semiconductors have greater conductivity depending on the amount of impurity atoms added during doping. Figure 28-1 shows the atomic structure of a silicon atom, which has an atomic number of 14, meaning 14 protons and 14 electrons. The first shell, or the K shell, has 2 electrons. The second shell, the L shell, has 8, and the third shell, the M shell, has 4 electrons, which are the valence electrons. All semiconductors, including silicon, have 4 valence electrons, which influence their electrical conductivity and how they combine with other atoms. The best conductors have 1 valence electron, while insulators have complete electron shells. A simplified drawing of a silicon atom highlights the 4 valence electrons and the +4 net charge of the silicon core due to 14 protons and 10 inner electrons. When silicon atoms group together, they form a crystalline structure by sharing their 4 valence electrons with neighboring atoms, creating covalent bonds. This electron sharing results in each atom having 8 valence electrons, which provides maximum electrical stability. At absolute zero, all valence electrons are locked in their covalent bonds, and no free electrons exist. However, at higher temperatures, some electrons gain enough energy to escape from their bonds, creating free electrons and vacancies called holes. These electron-hole pairs are thermally generated and increase with temperature. Silicon has fewer thermally generated electron-hole pairs than germanium, making it more stable at higher temperatures, which is why silicon is preferred in electronics. Although intrinsic semiconductors like silicon have few thermally generated electron-hole pairs at room temperature, they still act as relatively good insulators. Doping is a process where impurity atoms are added to an intrinsic semiconductor to improve its conductivity. Intrinsic semiconductors like silicon or germanium are not very useful in electronics on their own, so they are almost always doped to make them better conductors. When silicon is doped with pentavalent atoms such as arsenic, antimony, or phosphorus, it results in a lot of free electrons. This happens because the pentavalent atoms have 5 valence electrons, but only 4 are needed to bond with nearby silicon atoms. The extra electron becomes a free electron that can move through the material. This type of material is called an N-type semiconductor, where free electrons are the majority charge carriers. Even though the material is neutral overall, the doping creates some positive ions that are fixed in place. There are also a few holes or vacancies left by missing electrons, created in the material due to thermal energy. The free electrons are attracted to these holes and fill them, making the holes act like positive charges. In N-type semiconductors, free electrons are the majority current carriers, and holes are the minority current carriers. A trivalent atom is one that has three valence electrons. Examples of trivalent atoms are aluminum, boron, and gallium. When a silicon crystal is doped with a lot of trivalent impurity atoms, it creates many holes or vacancies in the material's covalent bond structure. This happens because each trivalent atom needs one more valence electron to complete its bond with silicon atoms, creating a hole where an electron should be. When millions of trivalent impurity atoms are added, many holes are created through the silicon. Since holes have a positive charge, we call this a p-type semiconductor. Although the p-type material is still neutral overall, it has more holes than free electrons. The holes are the majority charge carriers, and the free electrons, which are the minority charge carriers, are still present due to thermal energy. The trivalent impurity atoms create negative ions because they gain an extra electron, causing the atom to have more electrons than protons. These negative ions are fixed in place and can't move within the crystal. The p-n junction diode is a crucial semiconductor device that combines p-type and n-type materials. These two differently doped regions form what we call the p-n junction, where the p side is known as the anode and the n side is known as the cathode. Diodes allow current to flow in only one direction, making them unidirectional. The schematic symbol for a diode indicates the anode as the p side and the cathode as the n side. This structure controls the flow of electricity in circuits, making it essential for applications like rectification, signal modulation, and more. When a p-n junction is formed, free electrons from the n side diffuse across the junction to the p side, where they recombine with holes. This process creates positive ions on the n side and negative ions on the p side, forming a region known as the depletion zone. In this zone, all free charge carriers are removed, and the fixed ions create a barrier potential, or V sub B, preventing further electron flow. The result is a depletion region where the charge carriers are absent and the ions are immobile within the crystalline structure. This phenomenon halts the diffusion of electrons and holes, essentially creating a barrier that is crucial for the diode's unidirectional current flow. The barrier potential arises from the creation of ions at the p-n junction, which form a potential difference across the junction. For silicon, this barrier potential is approximately 0.7 volts, while for germanium, it's about 0.3 volts. This barrier potential prevents the diffusion of charge carriers, effectively stopping the current flow in one direction. While this potential cannot be directly measured using a voltmeter, it is essential for the functioning of the diode, as it controls the movement of current carriers across the junction and ensures the diode behaves as a unidirectional device. Forward biasing a diode means applying a voltage that allows current to flow through the device. In a forward bias p-n junction, the n side is connected to the negative terminal of the voltage source, and the p side is connected to the positive terminal. This applied voltage must overcome the internal barrier potential for current to flow. When the voltage is sufficient, it repels free electrons from the n side across the depletion zone and into the p side, where they recombine with holes. The electron flow on the p side moves toward the positive terminal of the voltage source, completing the circuit. For silicon diodes, this process requires a minimum of 0.7 volts. A resistor is typically added to limit the current. In the schematic symbol, the arrow on the diode points in the direction of conventional current, while electrons flow in the opposite direction. In circuit analysis, we often use electron flow for consistency. In a reverse bias p-n junction, the negative terminal of the voltage source is connected to the p-type semiconductor, and the positive terminal is connected to the n-type semiconductor. This causes the electrons on the n side to be pulled away from the junction and the holes on the p side to move away as well, increasing the width of the depletion zone. As a result, the diode is in a non-conducting state, effectively acting like an open switch with infinite resistance. In this state, no current flows through the diode under ideal conditions. The diode essentially blocks current in reverse bias. Diodes have clear polarity, meaning they must be installed with the correct orientation in a circuit. The anode is the positive side, while the cathode is the negative side. For forward bias, the anode must be connected to the positive voltage and the cathode to the negative. If installed incorrectly in reverse bias, the diode will block current or worse, be damaged. Correct installation is important for the proper functioning of the diode and to avoid damage to the circuit. Figure 2810 on the next slide is a graph of diode current versus diode voltage for a silicon diode. The graph includes the diode current for both forward and reverse bias voltages. The upper right quadrant of the graph represents the forward bias condition. The lower left quadrant of the graph represents the reverse bias condition. The volt-amp characteristic curve of a diode shows how current varies with voltage under both forward and reverse bias. In forward bias, a silicon diode allows very little current to flow until the forward voltage, or V sub F, exceeds about 0.6 volts. Beyond this, the current increases rapidly and the voltage drop remains around 0.7 volts. For germanium diodes, the sharp increase occurs at a lower voltage, around 0.3 volts. In reverse bias, there is a small leakage current, or I sub R, until the reverse voltage reaches the breakdown voltage, or V sub BR. The current increases sharply in this region due to the avalanche effect, where free electrons collide with valence electrons, creating more carriers and accelerating the current. Diodes should never be operated in the breakdown region as it can lead to damage. However, as long as the reverse current and voltage stay within the diode's power rating, the diode will recover. Rectifier diodes typically have breakdown voltages greater than 50 volts. Looking at the forward bias region of the diode's characteristic curve, we observe that the current, or I sub F, does not increase in direct proportion to the voltage. This confirms that the diode behaves as a nonlinear device, meaning doubling the voltage does not necessarily double the current. The DC resistance of a forward bias diode is calculated using the formula R sub F is equal to V sub F divided by I sub F, where V sub F is the forward voltage drop and I sub F is the forward current. For example, if the diode has a forward voltage of 0.7 volts and a forward current of 10 milliamps, its DC resistance would be around 70 ohms. To check a diode's condition, use an ohm meter. First, measure the resistance in one direction, then reverse the meter leads and measure again in the opposite direction. For a good diode, you should see high resistance in one direction, the reverse bias, and low resistance in the other direction, forward bias. For silicon diodes, the ratio of reverse to forward resistance should be very large, such as 1,000 to 1 or more. A shorted diode will show low resistance in both directions, while an open diode will show high resistance in both directions. When using an analog ohm meter, avoid the R times 1 range as it can damage the diode. The R times 100 range is ideal. For digital multimeters on the diode range, a forward voltage of 0.6 to 0.7 volts is expected for a healthy diode. Most digital multimeters cannot measure the forward or reverse resistance of a diode using the standard resistance ranges because they don't provide enough forward bias to activate the diode. These ranges are often referred to as low power ohm ranges. DMMs, however, have a special diode range that provides the necessary forward bias for accurate diode testing. When using this setting, the DMM displays the forward voltage drop across the diode instead of the forward resistance. For a good silicon diode, the forward voltage drop should be between 0.6 and 0.7 volts. A shorted diode will show very low or zero reading, while an open diode will display an overrange condition on both leads. When analyzing diode circuits, there are three different approximations we can use, depending on the level of accuracy needed for your calculations. The first approximation treats the diode as an ideal switch, which either acts as a perfect conductor when forward biased or an open circuit when reverse biased. The second approximation takes into account a small forward voltage drop, typically 0.7 volts for silicon diodes, in forward bias, giving more realistic results without excessive complexity. The third approximation is the most precise, incorporating the diode's dynamic resistance and the accurate current voltage relationship to achieve detailed calculations. The choice of approximation depends on how accurate the analysis needs to be for the particular circuit. The first approximation treats a forward biased diode as a closed switch with zero voltage drop, and reverse biased diode as an open switch with zero current. This simplified model is illustrated in figures 28-11A and 28-11B respectively. The ideal forward and reverse bias characteristics are shown on figure 28-11C, where the diode is assumed to have zero voltage drop in forward bias and no current flow in reverse bias. This approximation is often called the ideal diode approximation and is primarily used when only a rough estimate of the circuit's voltages and currents is required. The second approximation models a forward bias diode as an ideal diode in series with a 0.7 volt battery, reflecting the barrier potential of a silicon diode as shown in figure 28-12A. In reverse bias, the diode is still treated as an open switch with no current flow, as shown in figure 28-12B. The graph in figure 28-12C illustrates that the diode is considered off until the forward voltage reaches 0.7 volts, at which point the diode starts conducting. Once conducting, the diode is assumed to have a constant 0.7 volt voltage drop across it regardless of the current flowing. This approximation is more accurate than the first and is used when more precise answers are needed in circuit analysis. The third approximation of a diode takes into account the bulk resistance of the P and N materials as shown in figure 28-13A. This resistance causes the forward voltage V sub F to increase slightly as the current I sub F increases, and it's calculated using the equation V sub F is equal to V sub B plus I sub F times R sub B. In the reverse bias condition, the diode behaves like an open switch with a high leakage resistance, leading to a small leakage current as shown in figure 28-13C. The third approximation is the most accurate, accounting for bulk resistance and leakage currents, and is used for detailed circuit analysis. In this slide, we see how different diode approximations are applied to a circuit to calculate the voltage and current values. Figure A, the original circuit, represents the diode with its real-world characteristics and behavior. Figure B, the first approximation. In this simplification, a forward bias diode is treated as a closed switch, and a reverse bias diode is treated as an open switch. Figure C, the second approximation. Here the diode is treated as an ideal diode in series with a 0.7 volt battery for forward bias, while reverse bias still results in an open switch. Figure D, the third approximation, is the most detailed approximation, including bulk resistance in forward bias and leakage current in reverse bias. In this slide, we review the maximum ratings and electrical characteristics of semiconductor diodes. The breakdown voltage rating, or V sub BR, is the voltage at which avalanche breakdown occurs. It's also known as peak inverse voltage, or PIV, and exceeding this voltage can destroy the diode. The average forward current rating, or I sub O, specifies the maximum average current the diode can safely handle. If exceeded, the diode will be damaged. The maximum forward surge current rating, or I sub FSM, is the maximum instantaneous current a diode can handle in a single pulse. It's particularly important when diodes are connected to large capacitors, as the initial surge current can be high. The maximum reverse current, or I sub R, is the small reverse current that occurs when the diode is reverse biased. It is used in the calculation of reverse resistance, and datasheets often list the maximum reverse current. It's important to never exceed these maximum ratings in any application, as doing so could lead to diode failure and the need for replacement. This chart summarizes diode ratings and the importance of each. Rectifier circuits are used to convert AC voltage from the power line into the DC voltage required for most electronic equipment to function. Since most devices operate on DC power and the power line typically supplies 120 volts AC, this conversion is essential. The key components in this conversion process are rectifier diodes, which only allow current to flow in one direction. This unidirectional behavior of diodes enables them to produce a DC output voltage from an AC input. In the following circuits, we will assume that the diodes used are silicon diodes, which are standard in most power supply applications. The circuit shown here is a half-wave rectifier, which converts an AC signal into a pulsed DC signal. The transformer T1 steps down the AC voltage and provides the secondary voltage V sub S. When the top of the transformer secondary voltage is positive, the diode D1 is forward biased, allowing current to flow through the load resistor R sub L. When the secondary voltage becomes negative, the diode D1 becomes reverse biased, acting like an open switch, and no current flows through the load resistor. As a result, the output voltage consists of positive pulses corresponding to the periods when the diode is conducting current. When the AC signal is positive, the transformer supplies a positive voltage to the diode. During this positive half cycle, the diode is forward biased, allowing current to flow through the load resistor. During the negative half cycle of the AC signal, the diode is reverse biased and acts like an open switch, causing no current to flow through the load resistor. This results in a pulsed DC output, a series of positive voltage pulses that occur only during the positive half cycles of the AC input signal. In the transformer circuit, shown in figure 28-15A, we have a turns ratio of 4:1 between the primary and secondary coils. This means the voltage is stepped down by a factor of 4. The primary voltage is 120 volts AC, and the secondary voltage, V sub S, is 30 volts AC. The RMS voltage, or root mean square voltage, is 30 volts AC, as measured with an AC meter. To calculate the peak voltage, or V sub S peak, we multiply the RMS value by the factor 1.414. This gives us 42.42 volts as the peak secondary voltage. The peak-to-peak voltage, V sub P, which represents the total voltage swing, is calculated by multiplying the peak voltage by 2, resulting in 84.84 volts peak. These values are important for understanding the behavior of the rectifier, as they define the maximum and minimum voltages the circuit will encounter during operation. In this full wave rectifier circuit, the step-down transformer labeled T1 provides the secondary voltage. When the secondary voltage is positive, diode D1 becomes forward biased, allowing current to flow through the load resistor R sub L, while diode D2 remains reverse biased, blocking current. In the negative half cycle, diode D2 becomes forward biased and allows current to pass through R sub L, while D1 is reverse biased, blocking current. The key point here is that the direction of current through R sub L remains the same for both half cycles, providing a smoother and more consistent output compared to a half-wave rectifier. The graph of a full-wave rectifier shows the transformation of an input AC sine wave into a pulsating DC output. Notice how both the positive and negative half cycles of the AC input are rectified, producing a continuous output above the zero line. The output frequency is doubled compared to the input, which results in a smoother current flow. The peak value of the output waveform is the same as that of the input, but the ripple or fluctuations are less pronounced compared to a half-wave rectifier. In the full-wave bridge rectifier, the step-down transformer T1 provides the secondary voltage as well. When the top of the secondary voltage is negative, diodes D1 and D4 conduct, allowing current to flow through the load resistor R sub L. Diodes D2 and D3 are reverse biased and do not conduct. When the secondary voltage reverses, with the top being positive, diodes D2 and D3 conduct, allowing current to flow in the same direction through R sub L, while D1 and D4 are reverse biased. The result is a smooth, positive output voltage across R sub L, as both halves of the AC input contribute to the current flow. The graph of the full-wave bridge rectifier shows the conversion of an AC sine wave into a pulsating DC output. Both the positive and negative halves of the AC waveform are rectified, resulting in a continuous output that stays above zero. The frequencies of the output is twice that of the AC signal. The peak voltage remains the same as the input, and the ripple is smaller compared to half-wave rectifiers. This results in a smoother and more consistent DC output across the load. After rectification, the output from both half-wave and full-wave rectifiers is a pulsating DC voltage, which is not suitable for most applications. To smooth this pulsation and create a more stable DC voltage, a capacitor is connected at the rectifier's output. As shown in the example, a capacitor, like an electrolytic capacitor, with a value typically larger than 100 microfarads, helps to reduce the ripple, resulting in a smoother, more usable DC output for devices or for circuits that require stable voltage. In a half-wave rectifier, when the secondary voltage from the transformer goes positive, the diode conducts and charges the capacitor. The peak secondary voltage is calculated by multiplying the RMS value by 1.414, giving us 21.21 volts. After accounting for the diode's voltage drop, the capacitor charges up to a peak voltage of 20.51 volts. Once the secondary voltage drops below this value, the diode is reverse biased and the capacitor discharges through the load resistor. As the secondary voltage turns positive again, the diode conducts and recharges the capacitor to its peak value. This cycle generates a ripple voltage, with the capacitor discharging every 16.67 milliseconds for a 60 Hz input frequency. However, the peak-to-peak ripple voltage is undesirable, and ideally, we would want a steady DC voltage of 20.51 volts at the output. To reduce the ripple, we can increase the value of the filter capacitance. Like the half-wave rectifier, the full-wave rectifier output is smoothed using a capacitor. Figure 28-22A shows a full-wave rectifier with a capacitor filter at the output. During the positive half cycle, diode D1 conducts and the capacitor charges to the peak voltage of 20.51 volts. This voltage is maintained at the output, providing a steady DC voltage. Under ideal conditions, the capacitor smooths the rectified signal, resulting in a DC output voltage of 20.51 volts with minimal ripple. The difference between the half-wave rectifier in figure 28-21A and the full-wave rectifier in figure 28-22A is that C is charged twice as often in the full-wave rectifier. This also means that C has less time to discharge in the full-wave rectifier. In figure 28-22B, we see that the period for one cycle equals 8.33 milliseconds. Semiconductor diodes are not only used for rectification, but also serve other important functions. Two common special purpose diodes are the light emitting diode, or LED, and the Zener diode. LEDs emit light of various colors depending on the materials used, making them useful in displays and indicators. Zener diodes, on the other hand, are designed to regulate voltage, allowing current to flow in reverse once a specified voltage is reached, making them ideal for voltage stabilization. LEDs are made by doping elements such as gallium, arsenic, and phosphorus to produce diodes that emit light in various colors, including red, green, yellow, orange, and even infrared. The key to LED operation is the recombination of electrons and holes at the junction, which releases energy in the form of light. LEDs use semi-transparent materials to allow this light to escape, unlike standard diodes where the light is trapped. The voltage drop across an LED typically ranges from 1.5 volts to 2.5 volts, and the amount of light emitted increases with the forward current. For most applications, a current of 20 to 25 milliamps is ideal for providing sufficient brightness. A Zener diode is designed for operation in the breakdown region, unlike regular diodes that should not be operated near breakdown. The primary use of Zener diodes is in voltage regulation, where they are connected in parallel with the load to maintain a constant voltage despite fluctuations in current. When reverse biased, the Zener voltage stays nearly constant once the breakdown voltage is reached, and small variations occur due to Zener impedance. Zener diodes are rated by their breakdown voltage and power dissipation, and their power is calculated by multiplying the Zener voltage by the current. For example, a 12-volt Zener diode with a 30 milliamp current would dissipate 360 milliwatts. This concludes Lecture 1.